chance to take a look at 14.5? No? Okay, so some of you actually did that and said it was hard, a little bit challenging, right? So today we're going to actually spend time on it, and that's going to become a little bit easier for you guys. So 14.5, we're going to talk about the chain rule, okay? It sounds familiar to you guys. I use chain rule a lot in calculus, right? Do you guys remember the chain rule in Math 110A, calculus 1? Yes? Right?
Yes.
So if y is a function of x is a function of t, and they're differentiable function, so what will be dy dt? What does dy dt equal to? Yeah, so the dy dt here is going to be dy dx times dx dt, right? So that was the chain rule. That was the one that we had before. So this is like a ring of chain, and this is another ring of chain put together, looks like a chain, right? So that's called the chain rule. Today we're going to talk about chain rule for a function of more than one variable. So we have several versions of it. Now let's talk about the first version. And the first version over here deals with the case that z is a function of x and y. And each of the variable x and y is in turn a function of a variable t. You can try to think about when you drive a car, right? And then on the xy plane. And then this is the x coordinate, that's a y coordinate. And then maybe the z here is the speed, okay, or the velocity, right? And then x and y is a function of t. So at any given time, the x coordinate, y coordinate change as the time change. Then that function z is a function of t. It's indirect, okay? And z, you can represent that z here as a function. Okay, f of the x here is g of t, and then the y here is h of t. Both x and y are function of t. The chain rule gives a formula for differentiating z as a function of t. We assume that the function f is differentiable. So what's the chain rule in this case? So suppose z equal to f x comma y is a differentiable function of x and y. And think about like the velocity is a function of the position x comma y, okay? Where x is g of t, y equal h of t are both differentiable, okay? So this and this are both differentiable. The outer function f is also differentiable, okay? These two are differentiable function of t. Then this z is differentiable function of t. And when you try to differentiate z with respect to t, how do you find the derivative z with respect to t? That will be partial f partial x times dx dt has partial f partial y times dy dt, okay? So think about this one this way, okay? Suppose that here, if we hold the y here fixed, right? If we hold the y here fixed, then dy dt will be 0, okay? Then here, then will this disappear. Then the z here change, the way the z here change with respect to t will be the rate of change of that with respect to x times the rate of change of x with respect to t. This is just the regular chain rule. It's like the one that we mentioned before, right? And similarly, if you hold the x here constant as the t change, then that will be 0. And then this is just a regular chain rule in the one dimension, right? In the one variable. Okay, so you add these two together. Okay, it's a rate of change of z with respect to t. Okay, since we often write partial z partial x in place of partial f partial x, because z is this function. Z is equal to the function f of x comma y, right? So we can replace this by partial z, partial x, okay? So replace that way. So that becomes partial z, partial x times dx dt plus partial z, partial y times dy dt, okay? So that is the chain rule, okay? That was the first case when z is a function, is a differentiable function of x and y. And x and y are differentiable functions of t, okay? So you have this. Now how do you remember this, right? Okay, so I'm going to help you to remember this later on, okay, with a tree diagram, okay? There's a pattern right here, right? So if you try to find the derivative z with respect to t, so you take the partial derivative of z with respect to the first component, which is x, and then times the derivative of that with respect to t, okay? And then plus the partial derivative of that will get with respect to the second component, which is y, and then times the derivative of y with respect to t. Okay, so that's the one. Example real quick. The first example from here to here.
If z equals x to the second power y plus 3x y to the fourth, where x equals sine 2t and y equals cosine t, find dv over dt is t equals 0.
Okay, very good. All right, so in this example, we have z here as a function of x and y, right? It is a differentiable function of x and y, okay? It's a polynomial of x and y, so certainly it's differentiable, okay? And then x is a function of t, and it's also a differentiable function of t. Y is a differentiable function of t also. So we can apply the chain rule here, okay? To find dz dt when t equals 0. So let's just go straight to apply this. Okay, the chain rule gives dz dt equal to what? Let's fill in the blank. Everyone? What would that be?
dz.
Partial z, partial what?
Partial x.
Partial x? Okay, very good. Okay, keep on. Go on.
dt.
All right, so that will be partial z, partial x, right? For that one. And then what?
dx dt.
dx dt. Okay, good. Okay, and then the second part here,
Partial
partial z, partial
y.
y. Good job. And then what?
dy dt.
dy dt. You got it. Okay, good job. So that's the one. Now let's try to use apply this formula in this example. What is partial z, partial x? Which
2x.
means, what are we doing? We are trying to find the partial derivative of this with respect to x. So when we take partial derivative, we hold the other variable constant, right? So to calculate this, we're going to hold the y here to be constant, regard that as a constant. So what's partial z, partial x? Okay, just look at this chain first.
2xy.
2xy, you got it, okay? And then plus
3y to the 4.
3y to the 4, right? Yeah, you got it. Good job, okay? All right, so good job. Now, what's the dt?
2 cosine 2t.
This is going to be 2
2 cosine 2t.
cosine 2t, right? So 2 cosine 2t over here. Okay. Hey, you get the first part right. Okay, good job. So basically, you just apply the formula and you need to find partial derivative and also find dx dt here, right? Once you know how to do this, you can also do this part over here. So what's partial z, partial y? So we're going to hold this x here to be constant, and then we got this y here as the only variable here, right? So let's find partial z, partial y. What do we get?
X squared.
X squared? okay, plus
12x.
12x
12x.
y to the
third.
third power. Okay, good job. Okay. All right, nice. Okay, now what's dy dt?
Sine t.
dy dt is
Negative sine.
negative sine of t, right? Okay, nice. Okay, now we just we just applied the chain rule and found our first derivative. We find the derivative here using the chain rule that we just learned, right? So it's actually not too bad once you look at that. So as long as you keep clear what are we looking for. Okay, this is a positive derivative, and that's the derivative there. Okay? You guys did a good job. Okay, nice. Okay, now here is not necessary to substitute the expressions for x and y in terms of t. Okay, so do not substitute x equals sine 2t in here, y equals cosine t in here, because just keep it simple like this. So just keep it like this. The way that you figure the x and y here is you can substitute, because x and y are in terms of t, you can substitute the t value in both this function to find the corresponding x and y value, and then substitute in here. Okay? Right. So in this case, when t equals 0, what does x equal to? Sine of 0, which is 0, right? And when t equals 0, cosine 0 is 1. Okay. Therefore, okay, let's substitute here. So what should I put over here? 2 times 0 times what? 1 plus 3 times 1 to the 4 power times 2 cosine 2 times 0, right? Okay. Okay, you got it. Okay. And plus this one here, x is 0, y is 1. Okay. T is 0. So you just substitute. Okay. So what do you get? Okay, take a moment and do a calculation. What do you get?
Is it 6?
6? Yeah, you got it. Okay, good job. Nice. Okay. You guys just did the first example. Okay, very nice. Okay, good job, you guys. Okay, now we're going to consider the situation where z is a function x and y, but then this time x and y is not just a function of a single variable t, okay? X and y now is going to be a function of 2 variables, s and t. Then how does the chain rule look like, okay? Now, z over here is a function of x and y. X and y are functions of s and t. So z is a function of s and t indirectly, okay? So, and then we try to find positive z, positive s, okay? So we try to find the positive derivative of this z with respect to s over here. And then we also try to find the positive derivative of z with respect to t over here. So how do we do that? We know that in computing positive z, positive t, okay, if we compute this, we're going to hold the s over here fixed, right? So if you find the positive derivative of this with respect to t, then you're going to hold the other variable fixed, and then compute the ordinary derivative of z with respect to t, right? So therefore, we can apply the case 1 of the chain rule over here. Okay, if you hold the other variable, hold the s over here fixed, okay? If you hold the s here fixed, then it just become a function, z, s and y will become a function of a single variable, right? Of a single variable t, okay? If you hold the s over here fixed, okay? And then you can apply the case 1 over here, okay? So using this case 1, we get positive z, positive t, is positive z, positive x. Okay, remember the case 1 here, right? partial z, partial x, dx dt, right? But now instead of dx dt, because we have two different variables, s and t, so that will become partial x, partial t. Okay, so instead of this, we have partial x, partial t. Similar here, the partial z, partial y, and then instead of dy dt, you just put partial y, partial t. Okay, you're holding this x over s over here fixed. Okay, so it's not so instead of this ordinary duality here, you use a partial duality here and here. Okay. Okay. And then similarly, right, you use a similar argument, okay, to find partial, you can try to find partial z, partial s in a similar manner, okay, you use a similar argument, okay. So we put them together here side by side, okay. So this is the chain rule here, case 2, okay. So the case 2 is for z here is a differentiable function of x and y, okay? And then both x and y are differentiable function of two other variables, which is s and t, okay? Then if you try to find the partial duality of the z with respect to this s over here, this first variable right there, then that's equal to this. And if you try to find the partial duality of z with respect to t here, and that's equal to this, and then I say, wow, that's a lot of simple. How do you remember, right? Okay. We'll get to that, okay? So I'm going to have a diagram to help you remember. Notice that case 2 of this chain rule contains 3 types of variable, okay? What are the 3 types of variable? S and T, okay, S and T, those are independent variable, okay, independent variable. And then X and Y are function of S and T, right? So X and Y are dependent on this S and T. So it is the intermediate variable, okay, because X and Y is also, because Z is depending on X and Y, and then X and Y are dependent on S and T. So S and T are the independent variable. X and Y are called the intermediate, okay, intermediate variable. And then Z here is a dependent variable, okay? Right. So there are 3 types of variables here. Maybe we should look at a diagram to help us, right? So the z here is a function, is a differentiable function of x and y. X and y are differentiable function of s and t. Kind of like the, in biology, there's family tree, right? This gives this and this, and gives this and this, right? Okay. So remember, this s and t are the independent variable. X and y are the intermediate variable. Z here is the dependent variable. Okay, this one on top. Okay, depends on this and this. This one, this two depends on this and this. Okay. Okay. Now this diagram here actually can help you remember the chain rule of this second case. Okay. So if you try to find partial z, partial s over here, what do we do? So you can find this partial z, partial s here, which I highlighted. I circled them. Okay, partial z, partial s over here. If you try to find the partial duality of this with respect to s over here, then you just go down this path. Okay, to get to that. Okay, and also there's s over here. So it will be partial z, partial x times partial x, partial s. Okay, then you go down to this, and then you go down the other row here. Okay, so partial z, partial y times partial y, partial S get to this. And then we add them together. Add them together. So if you somehow have a hard time remembering this formula, then you can think about this diagram, right? How can I get from here to S? You go down this path, plus also you go down this path. Two different paths to do to get to that, right? Okay. Okay, now looking at this diagram, can you guys tell me what partial Z, partial T will be? What's partial Z, partial T will be? Partial Z, partial X
Partial X.
times what?
Partial X.
Partial X times, partial X, partial
T.
T, and then plus what?
Partial
Partial Z, partial Y,
Partial Y, partial T.
partial Y, partial T. That's it, right? Okay. So when you have two different variables, if you have more, the idea will be similar. You can use the tree diagram to help you remember the formula. Okay?
Do you mean more going this way? Like if you had
Now you have X, Y, and
Okay.
W, and then maybe S, T, and some V or something. Okay. Okay. So you remember the true formula, right? You can use the tree diagram to help you remember. How can I get from partial Z, partial T? You go this way, plus you go this way. Okay? Okay, and now we can consider the general situation in which a dependent variable U is a function of n intermediate variable, x1, x2, all the way to xn. Okay? Each of these xi over here, in turn, is a function of m independent variable, t1, t2, all the way to tm. Okay? So try to imagine the tree, right? So the tree over here, then you have, in this intermediate variable, you have like n of them. And then independent variable here, you have m of them. Then what will be the partial duality? Okay? So here's a general version for the partial duality. Okay? So suppose U is differentiable function of n variable. Okay? Those are the intermediate variable. And each xj is a differentiable function of m variable, okay, t1 all the way to tm. Those are the independent variable. Okay? Then the u, the dependent variable on top, right, is a function of all of this, t1 all the way to tm. Okay? And when you try to calculate the partial duality of U with respect to one of them, okay, say Ti, then how do I write that? Okay. Well, remember, we're trying to find the duality, partial duality of this with respect to Ti. So over here, you see, this also times Ti over here. Okay. So we'll have partial x1 over partial ti, partial x2 over partial x2, partial ti, okay, etc. Okay, all the way to this. But then this one here will be partial u, partial x1, partial u, partial x2, and you see the pattern over here, right? So look, this two match, and this two match. Okay, so you can see there's a pattern right here. Okay, maybe you think about this way. Okay, so partial u with the partial of the first component, right? And then times the partial duality of the first component with respect to ti, okay, etc. Okay, going this way. So that's a pattern right here. But don't worry, we are not going to go to. So I think we will maybe only go from x1, maybe up to 3 variable here, and this one maybe up to two variables. Okay. Okay. So, but it's good to know this general version. Actually, where's another? Okay, now we're going to talk about implicit differentiation. You guys remember implicit differentiation? Yeah, you okay? Okay, now I'm going to do this problem over here. Well, later on we're going to use one example and use the implicit differentiation we learned in 110A and also now in 110C. Okay. Okay. So implicit differentiation. Okay. So we suppose that an equation of this form, okay, the big F function of x and y equal to 0, okay? Think about this as a z, okay? Z equal to f of x comma y, okay? This function big F defines y implicitly as a differentiable function of x. The y over here is a function of x, okay? Now think about this is like the 3D, right? And this x coordinate, y coordinate. And think about the y coordinate is actually a function of x, okay? So y change here as a x here change, and it's a differentiable function of x. In that case, well, the z here equals 0. Think about that as like the z coordinate will be 0. So basically, it's on the xy plane, okay? And then y is a function of x. It's a differentiable function of x. Then this function f here, we can replace this y here by f of x because y is a function of x, okay? And for all x in the domain of this function, small f here, okay? If this outer function big F is differentiable, okay, we can apply the first case of the chain rule. Okay, now I put down the first case of chain rule right here to remind you that's the first case. Okay, remember the first case here, x and y are function of one single variable, right? Okay. Now if we put it this way, okay, then this and this are function of one variable, right? This is a function of x itself. This is a function of x, okay? So x and y are functions of one variable. So instead of t, it is x itself, okay? So the first and second component are function of one variable. First one here is the function itself, x. The second one here is a function of the variable x, okay? Now we can apply the chain rule, the case one here, okay? So to differentiate both sides of this equation, f of x comma y equal to 0, okay? So now I'm going to ask you guys, what happens if you differentiate this with respect to x? What happens if you differentiate constant with respect to x on this side? You get 0, right? Okay. So when I differentiate both sides with respect to x, okay, this side differentiate 0 with respect to x, we get back 0, right? So it's 2 0. So what about on this side? To differentiate this with respect to x. let me hold this. Okay, so we're going to apply the chain rule. What's the derivative this with respect to x? Partial f, partial x times what? dx what? dx, but in this case, what is the t? T is what? It is the x, right? Because here x and y are function of t, right? X and y are function of t, but then here x and y are function of x. So instead of dx dt, what should I put over here? dx what? dx dx. Yeah, dx dx. Okay? And then instead of dy dt, what should I put here?
df of x
dy
or dy df of x?
dy dx, right? So, because in this case, x and y are function of x. So insert the t here. So the x over there is actually in place of the t. Okay? So we place the t here by x over here. Okay. So we get partial f, partial x times dx dx. So we place the t and t here by x and x. This is d. That's the derivative of the function with respect to x. Okay, so you got this side over here. Okay. But what do we know about dx dx? What's the derivative of x with respect to x? That's equal to 1, right? Okay, that's equal to 1 right here. What about, okay, yeah, that's 1. Okay, so we're going to, this equal to 1. Now we can solve for dy dx. If this equal to 1, what is dy dx equal to? If I try to solve dy dx, what is it equal to? Negative.
Negative 1.
Partial f, partial x, divided by partial f, partial y, right? Okay, so this is what we got over here. So there's a negative sign right there. Okay. So in short notation, this is partial f, partial x. So it's the derivative of the function, partial derivative of the function with respect to x. This partial f, partial y is a partial derivative of the function with respect to y. So in short, dy dx is negative partial fx, partial fy. Okay. Okay. Now, to derive this equation 6, okay, we assume that fx and y equal to 0. Okay. Defines y implicitly as a function of x. Okay, so this defines y implicitly as a function of x. Well, what does it mean? Okay. For example, I can give you one example. For example, like this one over here. Okay, so this equal to 0, right? This equation, okay? The y here is actually implicitly is as a function of x, okay? So this y here is defined implicitly as a function of x, okay? So over here you didn't write y equal to a function of x, but it is implicitly. Okay, this equation defines y implicitly as a function of x. Okay, like that. Okay. Okay. Yeah, that's a lot of information today. So, slow me down if I'm going too fast. Okay? Am I losing you guys? Maybe more example. Okay, later. Okay. Now, remember that was equation 6, right? Okay. So this time, to find dy dx, okay, we can write it this way: is negative partial fx partial fy. Okay. This one over here. When do you have this formula? Okay. You have this formula as proven in advanced calculus, give condition under which this assumption is valid. Okay, what is the condition, okay? So it states that if the capital F function is defined on a disk containing a comma b, so in your mind, imagine there's a disk containing this point a comma b, okay? And f a comma b equals 0. So think about that it's on the xy plane with the z component to be 0, okay? And the partial duality in the y direction is not 0. So imagine that you have this vertical plane, right? That intersect with the surface, okay? The intersect with the surface, and then you have a curve, and then the tangent line, the slope of the curve at that point, a comma b, okay, is not equal to 0. And partial fx and partial fy are continuous on the disk. So the partial duality are continuous on the disk that containing this a comma b, okay? Then this equation fx comma y equals 0, define y as a function of x, and here the point a comma b, okay? And the duality of the function is given by this, okay? And given by this. I think you guys don't really have to worry about this, okay? So this condition for the function that you are given, they are going to be satisfied, okay, for the function that are given to you. Okay. So you can actually use this equation 6 to do that, okay? Now you say, well, how do you do that? Well, let's look at example. Example is better, okay? And let's start with something a little bit familiar to us first, okay? So we're trying to find the duality phi y prime if x cubed plus y cubed equals 6xy. How do we do that in Math 110A? You don't need to solve for y. Remember implicit differentiation? You can differentiate both sides with respect to x first, okay? And then later on solve for dy dx, right? So differentiate both sides with respect to x, okay? Let's differentiate this side. What do you get over here?
Now with respect to x.
3x
squared.
3x squared plus 3y squared times what? Y prime or dy dx, right? Okay. Good, very nice. Okay, so you got that. Okay, so this is the duality of the left side with respect to x, right? What about on the right side? What do you need? Well, we can pull out the 6, right? That's a constant multiple. And then to differentiate x times y, we need to use what? The product rule. Good job, okay? So that will be 6, parenthesis, and then times what?
Y.
Y plus x
F
times
dy dx.
dy dx. Yes, okay? So that's all. Yeah, you got it, okay? So using the product rule from here to here, okay? So we'll take out this constant multiple 6 and use the product rule. Differentiate, you got 6, right? Okay, good. Okay, and then now, well, we can make this equation a little bit simpler by dividing both sides by 3, right? Okay, dividing both sides by 3. All right, so you got something like this, right? Now let's solve for dy dx. So what does the dy dx equal to? So let's keep the dy dx on this side. So let's move this one to the other side. So we'll have what? X squared minus 2y in the numerator, right? And then divide by 2x minus y squared, right? Or opposite of y squared minus 2x. Okay, got it. Okay. Yeah, so you got this, right? So that's how we use implicit differentiation to find y prime in Math 110A, right? Now today we're going to do it a little bit different, okay? So in Math 110C, okay? So we have the same equation, okay? So for this equation, you can move every term to the left side, right? Okay. And if you move the 6xy to the left, okay, so that will be, this side here will become 0. And then you can define this capital F function as a function of x and y, okay, to be equal to this, okay, and that will be equal to 0. Okay, so basically you move this one to this side, and then let f of x comma y to be that, then that function here will be equal to 0. Okay. So you can think about that, the z component equals 0, okay, like that. Okay. So this is a curve on the xy plane. Okay. So, and then we can apply equation 6, okay, the function that we have satisfied those conditions. So we can apply equation 6, okay. So equation 6 says that to find y prime, or dy dx, it is opposite of the possibility of the function with respect to f divided by possibility of function with respect to y. Okay, let's do that. Okay, so what will be this possibility of this function with respect to f? Take a look here. What would this? We know how to find possibility, right? So we're going to keep the y here fixed, and then differentiate the with respect to x, right? So what's the possibility of this with respect to x? 3 x squared, right? And then what about this one? 0. And then minus
6y.
6y, right? Good. Okay, we got that one. Now get to the denominator. What's possibility of the function with respect to y? Okay. Now this time we're going to think about x here as a constant, right? So do it here 0, right? And then here 3y squared minus
6x.
6x. You got it. Good job. Okay. Now,
How come that's not an F? Oh, it looks like a Y.
yeah.
Yeah.
If you simplify this, right? Divide up and down by 3. Is it the same result that we got? Okay. From here to here, what did you do? Oh, we just divide by 3. Divide by 3 up and down.
So the denominator, it doesn't have to be a 6x. I'm confused.
I think it's supposed to be.
Okay.
Which one?
So for the denominator, it's 3y squared minus 6y, but it should be minus 6x.
On the left?
On the, oh, this is x. Yeah. You can call this typo. Actual particle test. This is x. You got it. Good job. Nice. Okay. Now you see that we got the same result. Okay. Comparing this method and this method, which one you think a little bit simpler?
Bottom one.
The bottom is simpler, right? So today we learn a new way to find dy dx. Okay, we can actually do that. You see the formula here? See, it actually switches x and y, right? So partial fx, partial fy, and then there's a minus sign there. Okay. So yeah, that was the formula. That's a little bit is worth remembering. Okay. Okay, good job. Are you guys ready to move on? Ready or not? Here we go. Okay, you here?
Now we suppose that z is given implicitly as a function z equals f of xy by an equation of the form capital F of x, y, z equals 0. This means that f of x, y, and of f of xy is equal to 0 for all xy in the domain of f. If f and f are differentiable, then we can use the chain rule to differentiate the equation f of x of y equals 0 as follows, which is this.
Okay, very good. Let's go through this together. All right, it's very similar to before. Okay, so what do we do over here? Okay, so what do we have? This time instead of a two variable, it's going to be a function of 3 variables. Okay, and you're going to have this capital F function with 3 variables here. Okay. And then you divide the z over here, okay, as a function of the first 2 variables, okay? The z is dependent on x and y. But then x and y are independent, okay, like that. Okay, so then you have this capital F function, okay, suppose that equal to 0 for all x comma y in the domain of the function small f. Okay, and the capital F and small f are differentiable. Then we can use the chain rule to differentiate the equation, this equation with respect to, I put it down here, with respect to x. Okay. Now, if you differentiate the right side, 0 with respect to x, we got that 0, right? Okay, now let's do this side. Remember, we're trying to find the derivative of this with respect to x, right? So remember the chain rule, right? So you have x, 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 because we're trying to find the derivative with respect to x. So x, and x. Remember the tree diagram, right? So you go down the tree diagram. So parcel f, parcel x, the first component, okay? And then parcel x, parcel x, okay? Now we took maybe draw the line. Okay, so this capital function. Okay, so parcel f, parcel x times parcel x, parcel x plus parcel f, parcel y times parcel y, parcel x plus parcel z. Parcel f, parcel z, and then times parcel z, parcel f. So we add this. Okay. But in general, you can see the pattern. Okay. So this is the first component, second, and third, right? So take the derivative, partial derivative this with respect to the first component, and then times this partial x, partial x. Take the partial derivative this with the second component times partial derivative this with respect to x. Okay, and then take the partial derivative this with the third component and then times partial derivative this with respect to x. So this is how you got this one here. Okay. But then we know that this is equal to 1. Okay, and what about partial derivative y with respect to x? Remember, the two are independent, right? So when we try to find partial derivative y with respect to x, then that is equal to 0, okay? So the y here is not the function of x. Okay. Okay. So when you have this equal 1, this equal to 0, then this term here disappears, right? This term here is 0. We can solve for partial z, partial x. Okay? So what does partial z, partial x equal to? Negative partial negative partial f, partial x divided by partial f, partial z, right? Okay. So which is this one over here. You guys follow? Okay? Okay, good. Similarly, we can also find partial z, partial y equal to this. Okay? Is there a pattern to remember this? Hey, you can notice that looks like z and looks like the x and z is switch, right? If you think about like this and this, right, and then x here and then z, okay, and d, y, and then here the z and the y, but then with the negative sign over here, okay. So try to think about a pattern to remember. Okay. Okay. The last paragraph. I'm going to ask someone. Juan, do you read from here to here?
Yep. Again, a version of the implicit function theorem stipulates conditions under which our assumption is valid. If f is defined within a sphere containing a, b, and c, where f, a, b, and c equals 0, f sub c of a, b, and c not equals 0, and f sub x, f sub y, and f sub 0 are continuous inside the sphere, then the equation f of x, y, and z equals 0. Define z as a function of x and y near the point a, b, and c. And this function is differentiable with partial derivatives given by equation 7.
Okay. Let's take a break and then we work on the practice